Okay, so I think I'm recording now, but it's certainly not very bright. It's dark in this room. Let me see if I can oops, that's not what I wanted. I want to share screen. Share screen. Uh, Genesis. Okay. So my apologies for the um, lack of illumination in this room. I'm in the kitchen of the local library, and the lights turn off automatically after a few minutes, so I just left them off. The genesis of a quantum impedance model, basically, it's what got lost in physics. How impedance matching was lost in quantum mechanics, and specifically at the very beginning, how it was lost in quantum electrodynamics, and then how the geometric representation, the other piece of the puzzle, was lost in mathematical physics. So the theoretical minimum here, we've got three assumptions. That's all there is. There's no free parameters. So when you're looking at this, it's just what's emerging from these three things. The vacuum wave function, we're looking at the algebra of space, the 3D Pauli algebra, SO3, more familiar to people in the SU2 representation. SU2 is the double cover of the SO3. It's a scalar, three vectors for the orientationals, three bivectors, and a trivector. So this eight-component vacuum wave function is the same at all scales. To physically materialize it, to manifest it, you have to add fields, and so we have both geometric quantization and electromagnetic quantization by introducing a coupling constant. The four fundamental constants that define the alpha, combinations of them permit us to assign topologically and geometrically appropriate unique magnetic and electric flux quanta to each of the eight components. And so we also have to introduce a scale of space here with the mass gap, the lightest charged particle, which is the electron. That's the mass gap in the model. And we model introductions with the geometric Clifford product, which is the sum of the dot and the wedge products. So multiplying two 3D wave functions together geometrically gives you a zero-dimensional object and a six-dimensional object, their difference in their sum. This is phase space. There's three space dimensions and three of quantum phase. Each of the orientations requires its own phase times the integral of phase. So space-time, doing the integral compacts this down to four-dimensional Dirac algebra, and time emerges naturally from the interactions. There's a nice paper here that discusses a lot of this in more detail if you're interested. How impedance matching was lost? Well, the Bajorkin and Drell, and also in his thesis, he was onto this. What got him confused here, and what's gotten everybody else confused, is that we have this topological inversion. The units of mechanical impedance are kilograms per second. You'd expect this means more mass flow if you have more kilograms per second, but it means less. And this inversion in SI units in any system of units basically is due to the topological duality of magnetic charge and electric charge. This Witten, this is a link to Witten's interview where he says this is his best work, was doing this duality space-time and quantum mechanics that Seeberg and Witten did. And this topological duality, what it does is, because the magnetic charge is so much stronger than the electric, if you replace the electric charge with h bar over g in these formulas, then what comes out inverts. So the Bohr radius is inside of Compton. And so this has many implications that we're not going to go into here, but it's something that's worth giving some attention to. The point here being then that this topology frustrated these guys. The concept of exact impedance quantization didn't exist until 1980 with the discovery of the quantum Hall effect. The topological impedance, the size or shape of the Hall bar only matters the number of holes in it, not its size or shape. This was easy because of scale invariant, but what we want, if we want to look at causal physics, then we have to have the scale dependent impedances. And finally, setting fundamental constants to unity. The theorists set Z equal to dimensionless unity and then forgot about it. So how it was found in quantum mechanics here, the vibratory pile driver. If you want to get stuff into the ground or pull it out of the ground, then There's two types of soils, the granular gravity or the cohesive clay. If you want to shake stuff in the ground, you got to go with gravity. If you want to use a delta function and bang it into the ground, well, the gravity, the granular structure makes a packing structure and catches it. You can't hammer it into the ground, but you can shake it into the ground. For clay, it sticks to the vibration, and you have to actually hit it hard with the delta function to get it to go in. So here we've got this mechanical analog of the Dirac equation. We've got a couple counter-rotating eccentrics. They pull together down, they oppose each other horizontally, they pull together up. It's transforming 2D rotation to 1D translation, an analog of the dot product or the Clifford product. And the Dirac equation of electron and positron spinors rotating in phase space. It provides a simple shortcut to calculating quantized electromagnetic impedance networks. If you had to calculate these electromagnetically, I don't know if it's possible. Maybe you can, but I don't know how to do it. And this is cool because mass is quantized in quantum mechanics. So you get these quantum impedance networks that govern the amplitude and phase of energy transmission. So designing, building, and operating these pile drivers, it gave birth to this paper here on the two-body problem and Mach's principle, where this strong epistemological argument was advanced, basically that was saying there's a piece missing in quantum mechanics. And it wasn't published. I submitted to the American Journal of Physics. Ed Taylor was very helpful, but the referee said no ideas. The timeline looks like this for classical and quantum impedances. We had these early instruments. These are classical here. And finally, the network analyzers, that was important. And then the transformation from analog to digital, that was a big step. These are theory, and here we have experiment. Here's when the mechanical impedance idea entered. And finally, to get the electron impedances, that was the last important step, 36 years between the two. So we're going to look at three examples here: the impedance match to the electron, the generalization to the elementary particle spectrum, and the Planck length. This is what the impedance match to the electron looks like. We've got a photon coming in here at 377 ohms, exciting the impedance of free space. That's what permits it to propagate and also defines the velocity at which it propagates. It encounters the inductive and capacitive impedances of the electron, which shift the phases in opposite directions, and it decouples the electric and magnetic flux quanta that comprise the photon. The electric flux quantum goes to high impedance, the quantum hole impedance, where there's an impedance match at the Bohr radius, and you can disassociate the hydrogen atom at that point. But this got lost in physics. It's not in the curriculum, the textbooks, or the journals. It's in the electrical engineering literature. In addition to that, you also need the quantized near field impedance of the electron. That got lost, and we see it here a little over a year after connecting with the photon impedance to the electron. And here we see the actual impedance network, what it looks like. So the scale is the same. This here is the unstable particle lifetimes multiplied by the speed of light. It's the coherence length, or you could say it defines the causal boundary of these particles. And this correlates with the nodes in the impedance network. And the reason it does so is because the impedances have to be matched for the energy transmission during wave function decoherence and collapse. So these are the various modes. You've got Coulomb mode here, scalar Lorentz mode here, dipole modes here, topological impedances are scale invariant. I don't know if we really need to say anything more about this, but anyhow, it gives an explanation for the unstable particle lifetimes that you won't find in the standard model. You can extend this from just the Compton wavelength down to the Planck length and find an origin for gravitational mass. You've got inflation here stopping at the Mach nodes at 10 to the minus 32 seconds. Chirality is in here, baryon asymmetry, and the origin of gravitational mass, again, in the impedance mismatch to the Planck length. And you can go the other way out to the boundary of the observable universe. And for instance, here at the Pauli scale at 10 to the minus 5 eV is where you find the axion. But it's impedance matched. We're bifurcated here. So everything goes to either very high or very low impedance, which could be part of the reason we have a hard time seeing the axion. And conveniently, what happens here from the Planck length to the Compton wavelength is a quarter wave resonator where the energy is transformed from the electric field to the magnetic field. And this behavior out here has to do with dark energy. So how the geometric representation was lost in mathematical physics, the claim is it's the universal language for mathematical physics. The Oersted Medal was awarded to David Hestenes for reforming the mathematical language of physics. And you can see here how the linkages, how the different differential forms, the different forms of mathematical physics are included in geometric algebra. The way it works for our purposes here is quite simple. We have a wedge product that increases dimensionality and a dot product that reduces. So that, for instance, if we have two vector bosons, W and Z, then the product, it changes the dimensionality. So two grade 1 vector bosons transform to grade 0 scalar and grade 2 bivector, the Higgs plus the top. And taken together, these four comprise a minimally complete 2D Clifford algebra, a scalar, two vectors, and a bivector. The sum mode of the two, the masses, is the top within a few parts per thousand. The difference mode is not the Higgs, it's the bottomonium, the dominant decay mode. So we don't see the Higgs mass here. I think this is partially related to why it's so difficult to calculate. The division algebras, again, there's only four: real, complex, quaternion, and octonion. And divide is a hard one. You need it for topology, for singularities, for dark matter, for duality. The eight-component Pauli algebra is minimally and maximally complete. So this is a natural wave function. It's the biggest you can have, and it's also complete, and it's the same at all scales. This is what a geometric wave function looks like. If you multiply two of these eight-component geometric objects together, you get an even algebra, which is the flavor eigenmodes, and then you get these odd modes, and this is the yellow is not an algebra. It doesn't have closure, and these are the transition modes. So finally, we're getting there. I think if we go ahead and assign the electric and magnetic flux quanta to the wave component, it breaks the degeneracy of the three vectors and the three bivectors. So we go from something that's 8-dimensional to 10-dimensional, 10 degrees of freedom, by adding the 2 additional degrees of freedom, the electric and magnetic fields. And that's the string in this model, we claim. So about the impedance model, the last item here, it has its origin in the S-matrix bootstrap, which eventually evolved into string theory here with the shift to the Planck length in 1974, when group theory basically, and the discovery of charm and the V minus C, all of this, I just swung everything into the standard model, and the string theory people ended up going up to the Planck length. So basically what we're saying is that the combination of geometric algebra and impedance quantization that contains this here. It's gauge invariant. The model is gauge invariant. Impedances regulate phases, and this replaces the covariant derivative. It's finite without renormalization because both ultraviolet and infrared, the matches are infinite. You can't couple to them. The confinement is the flip side of finiteness. The energy reflects back to the Compton scale. By the mismatches, it's asymptotically free. The modes are matched at the nodes. Energy flows freely. It contains the origins of mass from the mismatch to the Planck length for the gravitational, and from the electromagnetic field energies of the flux quanta. That's the inertial mass. It contains the four forces, dark matter and dark energy, and ChatGPT likes the impedance model. It explains the impedance model. It explains muon collider lifetime enhancement, and it explains massless neutrino oscillation. It explains many other things. So finally, I think I'm done here. So again, thank you very much for your time. I am very grateful for this opportunity. I want to, what do I want to do here? I want to stop share and stop